So, my name is Dr. Ch Apparao, working as an associate professor in mechanical engineering department. So, my subject name, that heat transfer. So, in last class we covered the radiation heat exchange between gray surfaces. So, in this class, just we'll see radiation heat exchange between gray surface with shields. It means the gray surfaces. So there are two gray surfaces. So in between these two, if we place shield, so what is the rate of heat transfer between the shield? So heat transfer between the two plates through the help of the shield. We'll see in this class. So I want to give the I want to refer the topics which are already covered in previous class. So you know that we derived this formula in last class. So it is the radiation heat exchange between two surfaces. We already derived. So we already derived the net Q net. It means rate of heat transfer between two surfaces. We already covered this one. The final formula is equal to, so this is epsilon place, so epsilon, so 1 minus epsilon 1 by A1 into epsilon plus 1 by A1 into F12, 1 minus epsilon 2 by A2 into epsilon 2. So this is the formula. So 1 minus epsilon 1 by A1 epsilon, that shows the surface resistance. 1 by A1 F2 shows the surface resistance. 1 minus epsilon 2 by epsilon 2 into area A2. So that shows the surface resistance of the second surface resistance. You know that. So Q net is equal to, you can rewrite like this one. We already derived this one. So 1 minus epsilon 1 by epsilon 1, 1 by F12. It means if you take if you multiply by A1 by A1, then we get this formula. So 1 minus epsilon 1 by epsilon 1 plus 1 by F12, 1 minus epsilon 2 by epsilon 2 into A1 by A2. So this is the formula, final formula we derived in the previous class. So based upon this formula, we derived the different conditions we saw. So you know that this is the electrical analog formula. It means initial heat energy, the final heat energy, and these are the resistances. Then the formula, you know that temperature difference, it means EB1 minus EB2. So emissive energy B1, surface 1 minus emissive energy surface 2 by. So total resistances we already covered in previous class. So we already saw this one. If the heat transfer between the small body to enclosed surface, it means this is a small body in a big enclosed surface or big room or anything. So in this condition, we already derived the formula, the rate of heat transfer here. So Q12. So based upon the previous formula, we derived this one. So this is the final formula is equal to, you know that. So it means Q12 is equal to sigma epsilon 1 into area into T1 to the power of 4 minus T2 to the power of 4. You know this formula, we derived this one. Okay. So you know that sigma Stephen Boltzmann law, epsilon 1 the emissivity of the body 1. So surface 1. A1 is the area of the small body. So because big enclosure means we neglect we consider the area of the big enclosure as infinity. You know, we already covered in the previous class. So this is the formula we derived in previous class also. So one more condition, we already saw this one. The heat transfer between any two surfaces, infinite parallel planes infinite means we consider those areas of both surfaces are equal. It means area A1 is equal to A2 is equal to A. So because infinite surfaces, so we considered area both are same, areas are same. So in this condition, here temperature of the first surface T1 and temperature of the second surface is T2, and the area both are same, and emissivity of the first surface epsilon1 and emissivity of the second surface is epsilon2. This one also we derived the final formula we got this one. This is the, so Q is Q12, it means rate of heat transfer from surface 1 to surface 2 is equal to, so sigma area into, so T1 T to the power of 4 minus, so T2 to the power of 4 by 1 by epsilon plus 1 by epsilon 2 minus 1. So this one, the formula we already derived in previous class also. Okay. So one more condition we already discussed. So this is the, so up to this just we covered in previous class. Now we'll see the heat transfer between two surfaces when a shield is placed between the two surfaces. So this one is the, so here surface 1, temperature of the surface 1 is equal to T1, emissivity of the surface 1 is equal to epsilon 1, the area, so it means we consider these are the plates are the infinite parallel plates, so automatically area A1 is equal to A2 is equal to A, you can consider this one. So next to surface 2, temperature T2 and epsilon 2 and area A. So in between these two surfaces we placed just one radiation shield. It means heat transfer takes place by the effect of radiation from surface 1 to surface 3. Surface 3 is nothing but radiation shield. So it means Q13 next to, so we will get one formula according to previous formulas. Next, radiation between the shield to surface 2. So Q32. So it means if you want to consider heat transfer between surface 1 to surface 2, Q12. So you have to consider the surface 1 to 3 and the 3 to 2. It means rate of heat transfer is same in both cases. You know this one. So we'll see here. So according to the first formula, what was derived based upon the heat transfer by radiation between the two plates. So you know that is a formula. So based upon the formula, we already derived the rate of heat transfer between two infinite parallel plates. So this is the formula. Okay. So this one is the formula. So first we are considering heat transfer between the surface 1 to 3. So it means heat transfer from surface 1 and 3. It means surface 1 and the shield. So then Q13 you can take, that is the Q13. It means the rate of heat transfer from 1 to surface 1 to shield 3. So then the formula is equal to sigma A T1 to the power of 4 minus T3 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. You know that because the temperature of shield is equal to T3, emissivity of the shield is equal to epsilon 3, area same. So areas of surface 1, shield and surface 2 are same. So then the formula is equal to Q13 is equal to sigma A T1 to the power of 4 minus T3 to the power of 4 by 1 by epsilon 1 plus 1 epsilon 3 minus 1. So similarly, we can take Q32. It means heat transfer between the surface 3 and the surface 2. So based upon this formula, you can write like this one, sigma T3 to the power of 4 minus T2 to the power of 4 into area by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So we can consider this one. So here already, so it was written. You can see and we can observe clearly this one. So that is Q32. So this one is the Q32. This is epsilon 3, epsilon 2. So this is the formula. So this one is the Q12. This is the formula, and the Q32. This is the formula. It means heat transfer between surface 1 and 3, and 3 and 2. So the final heat transfer between the two surfaces, surface 1 and the surface 2. So along with the shield, you can see this one. So Q12 is equal to, so sigma A into two resistances. We have to consider the two resistances. It means 1 by epsilon 1. So 1 by epsilon 3. Here also epsilon 3, epsilon 2. Okay. So it means if you consider this one, the resistances will be like this: 1 by epsilon 1 plus 1 by epsilon 2 plus 2 into 1 by epsilon 3 minus 1. So we can like consider like this one. So this one is equal to sigma A into initial temperature T1 to the power 4 minus T3 to the power T2 to the power 4. Okay. So this is the final formula. So it means if you consider the shield between the two surfaces, so this is the final formula for finding the rate of heat transfer from surface 1 to surface 2 along with the shield. So this is the similar thing, but here we are considering the same emissivities. So surface 1, surface 3 and surface 2 have same emissivities. So capacity of heat transfer. So epsilon 1 is equal to epsilon 3 is equal to epsilon 2 is equal to epsilon. So we are considering this is the one of just special case. We can consider this one. So here we know that Q12 rate of heat transfer between 1 to 3 is equal to rate of heat transfer between 1 to 2 is equal to rate of heat transfer between 3 to 2. So rate of heat transfer is same between two surfaces, or surface and shield, or shield to surface, both. So here just like we can consider this one. So because you know the previous formula, so previous formula is equal to Q12 is equal to sigma A. So T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So this is the formula. So based upon this one, just because epsilon 1 is equal to epsilon 3 is equal to epsilon 2 is equal to, both are same, all the epsilon. So here 1 by epsilon, 2 by epsilon. So the final formula will be like this one. You can consider this one. So finally Q12, the rate of heat transfer from surface 1 to surface 2. So along with the shield is equal to, so Q12 is equal to sigma A T1 to the power of 4 minus T to the power of 4 by 2 by epsilon minus 1 plus 2 by epsilon minus 1. It means both are same. It means 2 into 2 by epsilon minus 1. So you can consider this one. So finally this is the formula. So if there are n number of shields placed between the two surfaces, so Q12, this is the formula. Q12 rate of heat transfer from surface 1 to surface 2 by placing different number of shields. So if you consider n is the number of shields, then the formula is equal to like this one. So sigma A into T1 to the power of 4 minus T2 to the power of 4 divided by, so 2 by epsilon minus 1 into n plus 1. If you consider one shield, it means 2 into this one. So like this one. So 2 by epsilon minus 1, 2 by epsilon minus 1, just it means 2 into 2 by epsilon minus 1. So like this one. So if you consider one shield, this is the formula. Two shields, so this one is 3 because n plus 1. If you consider n is equal to 2, so 2 plus 1 3. If you consider 3 shields, so it means 4 into. So finally the number will be like this one. So the formula will be like this one. So Q12 is equal to sigma A T1 to the power of 4 minus so T2 to the power of 4 into area. So both in all conditions, all plates have same areas and similar emissivity also. So finally sigma A T1 to the power of 4 minus T2 to the power of 4 by so 2 by epsilon minus 1 into so n plus 1. So this is the formula. So n is the number of shields. So based upon this formula, we can derive the or we can solve the rate of heat transfer between two surfaces when those surfaces are just in between those surfaces, shields are placed. You can see. So this is the n is the number of shields. So here just like here we can see two types of formulas. So it means rate of heat transfer between two surfaces with shield or without shield. So this is the formula Q12. It means the rate of heat transfer from surface 1 to surface 2 with shield. With shield, this is the formula. So already derived in previous slide. So sigma A T1 to the power of 4 minus T2 to the power of 4 by so 2 by epsilon minus 1 into n plus 1. This is the formula for with shield. So shield either 1 or 2 or anything. So number of shields. Okay. Next to Q12 rate of heat transfer between two surfaces without any shield placed between the two surfaces. So this is the formula Q into area into T1 to the power of 4 minus so T to the power of 4 divided by so 2 by epsilon minus 1. So this is the formula. If the emissivities are same, so these are the formulas with shield and without shields. You have to remember these formulas for solving different numericals. If you ratio this one, so Q12 without shield by Q12 with shield or Q without with shield, then 1 by n plus 1. Okay. If you take just like n is equal to 1, it means 50% rate of heat transfer. You know this one. So n is the number of shields. We can identify the number of resistances also. You know that in the radiation process between the two surfaces, we can see three types of resistances. Two are surface resistances. One is the space resistance. You know that. So if we place any shields, just like n number of shields, the number of surface resistance, because you know that there are two types of this resistances. One is surface resistance and another one is the space resistance. Okay. So number of surface resistance, the formula for the number of surface resistance is 2n plus 2. 2n plus 2. And number of space resistance, so n plus 1. Okay. So for one shield, so there are 4 surface resistances and 2 space resistances. Okay. So in this way, just we can calculate we can identify the number of resistances between two surfaces when different shields are placed. Okay. So these are the formulas. We can remember this one. So finally, just to have discussed different formulas for the rate of heat transfer between the two surfaces when the surface positioning and just like positionings are different and the different conditions we saw this one. So based upon these conditions, based upon these formulas, we will solve some few numericals related to these things. So first one we'll see. We know that so first this numerical completely related to one surface. Okay, so one surface in which you know that irradiation G. So this surface you can consider this is the gray surface. If it is the irradiation, automatically some portion will be absorbed and some portion will be reflected. You know this one. So then because of the absorption energy, so this surface emits the emitting energy. So EB1, EB and rho G. We already discussed this one. So the addition of these two are called radiation. Okay. So here just like we have to find the radiosity. Radiation. This is the called radiosity. Radiosity is equal to rho Z plus E suffix B. So we already discussed this one. So based upon this formula, we have to find the radiosity. We'll see what is the numerical given here. Okay. So solar radiation of 1100 watt per meter square falls perpendicularly on a gray opaque surface. This is a gray opaque surface. So irradiation, falling energy. So that is the falling energy G is equal to 1200 watt per meter square. Okay. So emissivity epsilon is equal to 0.5. Okay. So if the surface temperature is, so surface temperature also given, T is equal to 50 degrees Celsius, you have to convert into kelvins. So 50 plus 273. So we have to add this one. Okay. Na? So 323 kelvins. So next, surface emissive power also given. It means EB1 or EB. Emissive power is equal to 600 watt per meter square. Okay. So here you have to find out the radiosity. What is the radiosity? So it is the opaque body. Emissivity is equal to just reflectivity. Emissivity epsilon is equal to rho is equal to, what is the value of emissivity? 0.5. Okay. So some portion will be reflected, rho G, and some portion will be emitted, EB1. You know this one, EB or EB. So radiosity J is equal to, you know the formula, rho Z plus and EB. You know that rho nothing but epsilon G plus EB. You know the formula of EB, emissive power of the black, emissive power is equal to, so rho G plus sigma into, if you consider area, just like T to the power of 4. So this is the formula. Then, so emissivity, what is the value of emissivity? Emissivity is equal to here 0.5 into irradiation. So falling energy. So solar radiation energy, that is the 1200. So plus sigma Stephen Boltzmann constant, you know that. So 5.67 into 10 to the power of minus 8 into, so temperature of the body 323 to the power of 4. So this is the value. If you solve this one, you will get the radiosity. So here already I have taken this solution in PPT. You can observe here also. So you can observe. So this is the, just like surface. This is the vertical falling. Sorry. So energy is falling vertically. So this is the vertical falling radiation energy. That one is the 1200 watt per meter square. Okay. So next to rosy. Rosy is equal to, it means some portion will be reflected. Rho is nothing but according to Kirchhoff's law, you know that rho is equal to emissivity. This one is equal to 0.5. So this is the 0.5. Sorry. Okay. Absorbivity is equal to emissivity. Absorbivity is equal to alpha is equal to emissivity. So you know that for opaque surfaces there is no transmission automatically. Alpha plus rho is equal to 1. Then rho is equal to 1 minus alpha. So alpha is equal to emissivity, 1 minus emissivity. So 1 minus 0.5. The value of rho is equal to 0.5. Sorry, this one. Okay. So then emissivity. So emissive energy is equal to epsilon into EB. EB is the emitting energy for black body. So this is the gray body. Then you have to consider this epsilon also. Then this one is the emitting energy for the gray surfaces. So then you have to consider all these things. Then for finding the radiosity, you know that radiosity J is equal to epsilon EB emitting energy plus reflecting energy rosy. So it means so rho epsilon into EB plus 1 minus rho is equal to 1 minus epsilon is equal to 1 minus 0.5 means 0.5 into G. So then the final values is like this one. Okay. So if you solve this one, so you will get this one. It means epsilon is equal to 0.5. So EB value also given. So that is equal to EB is equal to directly value will be given here. So 0.5 into surface emissive power. So that is the 600 plus rosy. Rosy is equal to 0.5 into 1200. So this is the 1200. Okay. So So it means 0.5 into 600 means this one is the 300 plus this one is the 600. So value is equal to 900. So you can see this one is the 900. So 900. So watts per meter square. So this is the value of this one. So we'll see one more numerical here. A sphere 10 centimeter diameter is suspended inside a large evacuated chamber. So this is the big chamber. Here one sphere is suspended inside a large evacuated surface. You can see this is the condition of small body in a big enclosure. So here it means big enclosure means that A2 you can construct this is infinity. So area as given. So we'll see this one. So 10 centimeters diameter. So D is equal to 10 centimeter. Then R is equal to 5 centimeter. If you convert this one 0.1 meter, so this is the 0.05 meter. So this one is the radius. Okay. Next, whose walls? So suspended in an evacuated chamber whose walls are kept at 300 Kelvin. So temperature of T2. It means enclosure surface temperature T2 is equal to 300 Kelvin. If the surface of the sphere has emissivity, so emissivity epsilon 1 is equal to 0.8. So has been given and is maintained at 500 Kelvin. So the temperature of a small body T1 is equal to 500 Kelvins. Okay. So it means two surfaces, surface 1 small, surface 2 big. temperature 500 Kelvin, area, so pi r square pi into r is equal to 0.05 whole square. Next to emissivity is equal to 0.8. Here a to infinity you can take because large enclave area no need to construct. Temperature T2 is equal to 300 Kelvin. Okay. So next to epsilon no need to construct here epsilon because surface is very large. Then you know that this formula, when the small body and the radiation between the small body in a big enclosure, just like a small object and big room. So for this one, we know the formula Q1 to rate of heat transfer from small body to big enclosure. That is a sigma into area A1 into epsilon into T1 to the power of 4 minus T2 to the power of 4. This is the formula, you know this one. Sigma 5.67 into 10 to the power of minus 8 into area. Area is equal to pi into 0.05 whole square. Epsilon is equal to 0.8. Okay. So into temperature T1 is equal to 500 Kelvin, 500 to the power of 4 minus T2. So enclosure temperature is equal to 300 to the power of 4. So if you solve this one, we will get the final answer like this one. You can see here. So this is a small body suspended in a big enclosure. So diameter of this small body 0.1 meter, converted in meters. Radius also 0.05. Temperature 500 Kelvin, and epsilon emissivity of this small body is equal to 0.8. Then this is the surface too. It means big enclosure. Area you can consider, because this is the big enclosure, you can consider area as a infinity. Temperature T2 is equal to 300 kelvins. Then you know the formula epsilon 1 into sigma A1 into T1 to the power of 4 minus T2 to the power of 4. If you substitute the value of epsilon 1, that is a 0.8, and area 4 pi. So this is the sphere. Just we have to remember this one. 4 pi r square, 4 pi into r is equal to 0.05 whole square into sigma. The value of sigma is equal to 5.67 into 10 to the power of minus 8 into temperature of the small body 500 kelvins. Temperature of the enclosure 300 Kelvin. If you solve this one, we will get this value 77.5 watts. So in this way, just like we can solve different numericals which are related to like small body in a big enclosure. So just have given one numerical, one model numerical which is related to small body in a big enclosure. We'll see one more numerical. So this is an electric heating system is installed in the ceiling of room. So in a room, okay. So room measurements also given. So length of the room, that is 5 meter. L is equal to 5 meter, and width or breadth is equal to 5 meter. Height is equal to 2.5 meters. Okay, so the temperature of the ceiling temperature also given. So it means we can construct, this is the ceiling is surface 1, and room walls surface 2. So it means here heat transfer takes place from the ceiling to surface surrounding room walls. So 4 walls. So 4 into wall areas we have to construct this one. So first of all, we understand the numerical what was given here. Room measurements has been given. The temperature of the ceiling. So temperature of the ceiling is equal to 315 Kelvin. So whereas under equilibrium condition, the walls are at, so walls temperature also given at equilibrium condition. This means four walls have same temperature, that is they maintain the same equal temperature, that is 295 kelvins. If the floor is non-sensitive to radiation, so no need to consider the floor because the floor is non-sensitive to radiation. It means there is no radiation heat transfer by radiation from the floor to other surfaces. Just you can neglect this one. Then the emissivities of the ceiling emissivity, that is epsilon 1 is equal to 0.75, epsilon 2 is equal to 0.265 respectively. Calculate the radiant heat loss from the ceiling to wall. It means, so ceiling to wall. So here walls means four walls are there. You have to construct all the surface of the walls. It means 4 into wall surfaces. Wall surface means breadth into height, B into H. You will see the diagram also. First of all, you can understand properly. Okay. So diagram of the ceiling and walls. Okay. Here, just like in this numerical, heat transfer takes place from the ceiling to surrounding walls. So it means first surface you can consider the ceiling, and another surface consider the walls of the room. Okay. So here, just like this one is the ceiling, surface one, room walls. So we have to consider all the walls of the room, 4 walls. So that is the surface 2. Here it means heat transfer between the surface 1 and the surface 2. It means heat transfer between the ceiling and the walls. So you can see here also otherwise. Ceiling to surrounding walls. So here floor is a non-sensitive to radiation. No need to consider this one. Floor. So all the room walls considered as one surface and ceiling as one surface. So it means surface 1, it means ceiling, surface 2 wall surfaces. Just to consider this one. Okay. Next, you know the formula for this one, the rate of heat transfer between the two surfaces. This is the formula, you know this one. Sigma A1 into T1 to the power of 4 minus T2 to the power of 4, 1 minus epsilon 1 by epsilon 1 plus 1 by F12, 1 minus epsilon 2 minus epsilon 2 into A1 minus A1 by A2. You know that areas first of all. Area of ceiling. Area of ceiling means just like length into breadth. This is 5, this is 5, height is equal to 2.5 meters. You can consider this one. Okay. So it means area of the ceiling A1 is equal to 5 into 5 meter square. So 25 meters square you can consider this one. So area of the rooms. So 4 walls are there. 4 into area of the wall. Area of the wall is equal to 5 into 2.5. Okay. So this one is the areas 1 and areas 2. So then you know that all the required values, you know the epsilon 1 is equal to ceiling emissivity is equal to 0.75. Epsilon 2, so just like emissivity of surface 0.65. So these are the values. You know the area, and you know the sigma value 5.67 into 10 to the power of minus 8. Temperature of the ceiling. So T1 is equal to 320. Ceiling is equal to 315. So in this numerical 315 Kelvin, and room temperature is equal to 295 Kelvin. So all these values, you know this. If you substitute all these values in this formula, area is equal to 5 into 5, 25. 5.67 into 10 to the power of minus 8. T1 is equal to 315 to the power of 4 minus 295 to the power of 4 by 1 minus epsilon 1. Epsilon 1 is equal to 0.75 by 0.75. F12, you know that between the two surfaces, if you apply the formula, F11 plus F12 is equal to 1. So 1 1 here, 1 1 is equal to 0, then F12 is equal to 1. So the value of F12 is equal to 1. So this is the 1, and you know the value is epsilon 1 and epsilon 2 also, area 1 and also area 2 also. If you substitute all these values in this formula, then we will get the final answer. It means the rate of heat transfer between the ceiling and the surrounding walls, Q12. So Q12 is equal to, this is the formulas. It means sigma A. Here if you consider the sigma A here, this is the R1, this is the R2, this one is R3. Okay, if you solve this one, automatically you will get this formula. Okay, otherwise if you consider area here, so 1 by A1, 1 by here also 1 by A1, here 1 by A2. So you can consider this one. So finally, so Q12 is equal to sigma T1 is for 4 minus T2 is for 4 by total resistances. Resistance R1, resistance R2 and R3. R1, R2 and R3. If you solve this one, we will get a final answer, that is the 1920.39 watts. So this is the value. So in this way, just like we can calculate different heat transfer rates, rate of heat transfer by radiation between two surfaces, that ceiling to surrounding walls, or floor to surrounding walls, or surface one surface to another surface. So this way, just like we can calculate the rate of heat transfer. So based upon the formulas which are derived in previous slides. Okay, you can use this one. So one more numerical we will see, and we close this session. So two parallel infinite gray surfaces are maintained. So these are two parallel infinite gray surfaces. Infinite means you can consider areas, both areas are same. Okay, so gray surfaces are gray, are maintained at temperatures. Temperature of first surface. So this is the surface 1. This one is the surface 2. So first surface T1 is equal to 400 Kelvin. Surface 2 T2 is equal to 500. Just you can take this one is equal to T1 is equal to 500. So heat transfer takes place by higher temperature to lower temperature, 500 Kelvin. So this one is the 400 Kelvin. Okay. So the temperature of hot surface. So here we can consider this is the hot surface, this is the cold surface. Okay. So the temperature of the hot surface is increased. One more condition. First of all, you have to consider and you have to find out the Q12. So based upon these temperatures, then you have to again you have to find out the Q12. So Q12 dash, it means based upon the increased temperature. It means so T1 is equal to 600, T2 is equal to 400, same. It means because hot surface is increased to 600 Kelvin. By what factor is the net radiation exchange per unit area increased? So here area Q by A how to find out. So heat flux you have to find out. Assume emissivities of the colder and hotter surface to be. So emissivity value is also given. Epsilon 1 is equal to 0.9 and epsilon 2 is equal to 0.7. So these are the values. Okay. So just based upon this values, you have to find out the radiation rate of heat transfer between two surfaces. First initial condition, just to have to find out the rate of heat transfer by radiation between two surfaces at these two surfaces, these two temperatures. Again, you have to find out the rate of heat transfer when the surface of hot surface or the hot surface temperature is increased to 600. It means 500 to 600 will be increased. Then automatically, then you have to find out the rate of heat transfer at that particular temperature. Then you have to compare this one. So you'll see first of all. So this one is the two infinite parallel plates, gray surfaces. So next, the formula, if the rate of heat transfer between two surfaces infinitely parallel gray surfaces, then the formula Q12 is equal to sigma A into T1 to the power of 4 minus T to the power of 4 by 1 minus epsilon 1 and 1 minus epsilon 2 minus 1. Otherwise, you can write like this, and Q12 by A area, unit area, just like sigma into T1 to the power of 4 minus T to the power of 4 divided by 1 minus 1 by epsilon 1 plus epsilon 2 minus 1. So based upon this formula, just first of all you have to derive this one. So Q12 is equal to sigma 5.67 into 5.67 into 10 to the power of minus 8 into T1. What is it? T1 is equal to 500 Kelvin, 500 to the power of 4 minus T2 is equal to 400 to the power of 4. So divided by, so 1 by epsilon 1, 1 by 0.9 plus 1 by 0.7 minus 1. Then the value, you can find out the value. So here just like we'll see, the same steps here given. So Q12. So Q12 is equal to sigma T1 to the power of 4 minus T to the power of 4 into area by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Then you can write like this one, Q12 by A. So then sigma is equal to 5.67 into 10 to the power minus 8. Temperature 500 to the power of 4 minus 400 to the power of 4 into area. You can write this A here. Then 1 by epsilon 1, 1 by epsilon 1, 1 by 0.27 plus 1 by 0.9 minus 1, because the first surface you are considering 0.7, because according to this temperature ordering, so you can take no problem here. Then the second condition, if the temperature of hot surface temperature is equal to 500 Kelvin has been given. If we increased this temperature from 500 to 600, what would be happened? We'll see this one. Then the formula, then the temperature, just like revised temperature of first surface T1 dash is equal to 600 Kelvin and T2 same temperature. Then the same formula Q12 dash is equal to sigma Q12 dash by area into sigma T1 to the power of 4 minus T1 dash to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Epsilons are same. So sigma, we know that sigma value is equal to 5.67. 5.67 into T1 is equal to 600 power minus T2 is equal to, what is the T2? Same temperature, 400 to the power of 4 by epsilon 1 by 0.7 plus 1 by 0.9 minus 1. So if you solve this one, just like we will get the values, just you can see. So rate of heat transfer at revised temperatures. So this one is the value. We will get the value is equal to 3830 watt per meter square. So here just like initially this one, if the temperature is raised, the just rate of heat transfer or radiation flux is equal to 3830 watt per meter square. Then we'll see the just increasing growth, just like Q1 dash minus percentage, Q1 dash minus Q1 2 by Q1 into 100. So it means 3830 minus 1359 by 1359 into 100. So it means nearly 18%. So it has been increased. So in this way, just like you can calculate the rate of heat transfer between any two surfaces, either surface are parallel infinite or any just like finite surfaces also, we can solve this numericals based upon the formulas which are already derived in the previous slides. Okay, thank you for listening this class. We will see next few more numericals based upon these formulas. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.